Okay, thank you everyone for joining our webinar. My name is Neeraj Mehta and I will be your host. With me is Dr. Shashankara. Thank you all for attending. I will start by giving a brief intro to our company and our product and our webinars for those of you new to CPFD software, and then I'll turn it over to Shashank for a detailed discussion of the application model. So today's webinar is the first in our application model webinar series, and we will be discussing our Circulating Fluidized Bed Combustor application model. This webinar is being recorded and will be available for playback later today. For all of our past webinars, you can head to our website and go to the webinar section where you'll be able to see webinars discussing our latest releases, our customer success stories, and others. During the webinar, you are free to ask questions. We highly encourage you to use the GoToWebinar panel to ask questions. As you can see in the photo here, you'll be able to go to the question section and type in your question. Our staff will log all questions being asked, and then at the end of the webinar, we will have a Q&A session where we will answer whatever questions you provide. If we do not get to your question during today's webinar, we'll make sure to follow up with you afterwards to give you any answers that you may need. So for a brief introduction for CBFD software, CBFD is a company that's advancing multi-phase simulation. We work in simulating fluid particle systems, primarily fluidized bed reactors, but not limited to those. Our flagship product is Barracuda Virtual Reactor, which simulates the fluid dynamics, particle physics, heat transfer, and chemistry in industrial scale fluid particle systems. The software is used for a variety of purposes, including optimizing, troubleshooting, design, maintenance, research and development, across a wide variety of fields worldwide. Barracuda Virtual Reactor is the only software on the market that handles and resolves these types of simulations at a industrial scale, including the physics and chemistry. It resolves both fluid and particle phases independently and coupled. This software is a full software package, so it includes the preprocessor, post-processor, grid gen, and solver. It is very flexible in deployment. It can be used on-premise or on the cloud, and what is powerful for its abilities for resolving these calculations is that it's parallelized on NVIDIA GPUs. And this parallelization is baked into the software, so anytime NVIDIA releases a new top-line GPU, those gains are immediately realized within the software. Barracuda Virtual Reactor is, there are two main domains for simulations for Barracuda Virtual Reactor. The first being gas fluid domain. So this is, and this is true for both gas and for liquid domain, but in these simulations, there's no limit to the number of materials that can be defined. So that's unlimited number of particle species. Each particle species has its own material composition, its own particle size distribution, and its own ability to interact with the fluid and other particles in terms of chemistry. There's no limit to the number of fluid species that can be defined, and then liquid can be present in the system in terms of droplets and as well as liquid coating for solid particles. These phases are all tightly coupled, so they can all engage in heat transfer and chemistry. So fluid, particle, particle, all can engage in heat transfer and in chemical reactions. And then likewise, a new development in the past 5 or so years is the ability to simulate liquid domain. So this would be liquid phase with solid particles, and then as well the gas can be present in the form of bubbles. And again, there's no limit to the number of species that can be defined. So it's an unlimited number of bubble species, unlimited number of particle species. Each independent particle or bubble species can have its own material compositions, its own size distributions, and likewise as the gas domain phase, all the phases are capable of interacting with each other in terms of chemistry and in terms of fluid dynamics and particle physics. So the fluid acts on the particles with drag, the particles displace the fluid, and again, it's fully tightly coupled chemistry and heat transfer. The particles, bubbles, are discrete Lagrangian entities. The fluid is an Eulerian phase, and they are both resolved independently against the grid. And as I said before, they are coupled, so they affect each other across each time step. And so that is a quick introduction to CPFD software and our flagship product. If you are unfamiliar or you're new to the software and new to our offerings, feel free to shoot us an email to learn more. But with that, I would like to discuss our application models, which is what this new webinar series is about. So these application models are a new development from our company over the last year or so. And they're sample use cases, but they're based off of actual industrial scale applications. If you are a current licensee of Barracuda Virtual Reactor, you can go to our website and you can download, run, and customize to your heart's desire these models yourself. So they're available now. There's 9 or so application models available right now. And again, you can download them right now. If you open up these application models, they have instructions for post-processing to get you started on how to visualize these models. And they also include references to the literature that was used in their development. So you can find these papers yourselves and go comb through them. And the idea for these is twofold. For new users, it's a great way to learn about the software and see what typical operating conditions might look like for a related application, and learn how to get started, what knobs to turn, what parameters to tune, what is kind of a realistic way to set up an industrial scale reactor. And then for experienced users, it can kind of give a guide for what are best practices. What would our expert engineers recommend be the parameters and the setup for a realistic real world application. This is the first session in our webinar, and without further ado, I'll hand it off to Shankara. Today's webinar is the Circulating Fluidized Bed Combustor, but we have application models across several industries, including hydrogen production, cement, oil and gas upstream, and we have more applications on the way, with new ones being developed every quarter. And now I'll give an introduction to Shankara. Dr. Kara has over 18 years in experience in thermal fluid sciences and CFD applications. His experience includes roles at Baker Hughes, ANSYS, Pacific Northwest National Lab, Oregon State University, and the University of Tennessee. Shashank has provided technical support to CFD clients. He's researched and developed technical solutions for the energy industry, performed engineering consulting work, and he's trained customers in commercial software tools. His experience is in solving complex thermal fluid problems using multi-phase Eulerian, Lagrangian, and discrete particle method software tools. He's in a unique position to strengthen and broaden application areas for Barracuda Virtual Reactor, and we were so happy to have him on the team. Shashank defended his PhD in mechanical engineering at the Oregon State University, and he has as well a bachelor's in biomedical engineering and a master's in engineering science. We're excited. We've been excited to work with him these past couple of years, and we're excited for him to be able to show you what he's been working on. So without further ado, Shashank.
Yeah, thanks very much. Thanks for the introduction here. Let me start sharing my screen here. Okay. Can you see my screen, Raj?
Yes, we can see your screen.
Okay. All right, let me get my laser pointer up here. Firstly, I just want to take a moment here and thank everybody for taking their time to join this meeting. I know we have attendees all over from the world tuning in for this presentation. As Inaj was pointing out, this is the first of our presentations in our webinar series, and we are quite excited to bring this over to you. So without any further delay, let me jump straight into the topic here. What we are looking at today is an application model for circulating fluidized bed combustor. And before we jump into more details, let's just get the higher level view down here in terms of what is a CFB, or a circulating fluidized bed combustor, right? Essentially, it's a furnace used to burn a whole bunch of solid fuel in it. The difference from a conventional furnace is that the reactor in this CFB happens to be a fluidized bed reactor. So as I show in the picture down here, you basically have your solid material. This can include your fuel. This can include your bed materials such as ash, which is circulating, carrying out the heat transfer in the system. You can also have sorbent as solid material added to capture pollutants. So, all the solid material is placed inside the reactor. Then you have basically primary air coming in from the bottom of the reactor. Now, this air serves two purposes, right? One is it fluidizes the solids. When we say fluidized, for those who are not familiar, what we're talking about is the solids almost start behaving like a fluid, essentially. The motion of them, and then and then as you move up sort of this reactor or this riser section of the CFB, you have several secondary air injection points, right? And the idea is to do a stage combustion with that, and we'll come to that in a second when we go over some of the results here. But that's essentially the idea. You start fluidizing the bed. If the fluidization operation is working properly, you basically see that there's a lot of well mixed system, which ensures that there's proper contact time between the gas and the solid, helping with the combustion process. Again, if the solids are circulating well enough, you should see sort of a uniform heat distribution in the riser without any heat spots in it. And once this process happens, the combustion takes place. What they typically do is, the heat from this combustion is recovered through various heat transfer surfaces. So you have heat transfer surfaces in the riser section, in the separator, and so on. Right. So again, key advantages to me, one of the fundamental advantages for a CFB is the diversity of fuels that can be used. So you can have like low-grade coal, but you can as well as replace that coal with industrial waste, municipal solid waste or biomass. And you can actually combine these fluids as well. You don't necessarily have to have a single fluid fuel inside the system. So when you combine these, and if you can get the fluidized bed reactor to operate properly, you basically have a pretty high combustion efficiency for a CFB. Not only that, basically the combustion happens at relatively lower temperatures, which actually means there's less chance of NOx formation. And even if you do form some NOx, like I was talking about, you can always throw in some sorbents in the system to capture some of that, pollutants even before, they leave the reactor. So with that said, what are the applications for such a CFB reactor, right? The obvious applications are, once you recover the heat, that can be used for power generation. It could be used for steam generation, and then that potentially can be used downstream in several industrial processes such as paper mills, chemical plants, and so on. The other big advantage is basically waste to energy. So as I was talking about, it's literally, you can combine fuels down here. Essentially bring in your municipal solid waste, or maybe bring in some organic matter, and you can start using that to for your combustion process here, essentially. With that said, with any type of industrial equipment, there are always some operational as well as design challenges, right? The first thing obviously is just the physics involved in the system. So you're talking about the hydrodynamics of basically the gas and the solids interacting with each other. On top of it, you also have reactions which are taking place. These reactions are taking place both in the gas phase as well as in the solid phase itself. Once, let's say, you do operate the reactor well, you have to deal with the problem of emissions control. You want to sort of minimize your pollutant formation, and if you do form pollutants, you want to make sure that you're trying to capture them before they leave the reactor. Essentially, if the fluidization operation is not happening properly, then that basically leads to inefficient mixing, so your combustion is not taken properly, and then also can lead to hotspots. And anytime there is high velocity gas with particles, you always run into the issue of erosion, essentially. So that's also something to deal with. And this is where CFD modeling can actually help out. Truly, if you are able to build a 3D CFD model which is running transient in time and can account for these complex hydrodynamics as well as reactions happening, then that actually provides a lot of insight essentially into the operational aspects of your reactor, into how the design that is the design working as it's intended to be. And so sort of once you sort of go through that process, and either you troubleshoot them, or maybe your reactor is already working pretty well, then you can start thinking about scaling up essentially, right? So you can start thinking about scaling this up from a lab scale, pilot scale to industrial scale. So maybe you see very good operation in your pilot scale, but you want to make sure you see the same thing when you move up in terms of the the sizing of the reactor itself. So several advantages there with CFD modeling. And that said, next we specifically zone in and we look at what is the CFBC solution that Barracuda virtual reactor offers. And so going back to what Niraj was saying, so Barracuda essentially uses a methodology called MPPIC. The solver is built on this numerical discretization scheme. MPPIC stands for multi-phase particle and cell method. The idea is that essentially inside of this framework, we are actually tracking particles. These are numerical particles or computational particles, also referred to as clouds. And we're dynamically tracking a four-way coupling between the particles as well as the fluid. So by four-way coupling, I mean that both the particles and the fluid phase can exchange mass, momentum, energy back and forth, essentially. And not only can we do this on a small scale, but typically Barracuda computational particles inside some of our use cases could run into tens of millions, essentially. And these tens of millions of computational particles represent probably billions and trillions of real particles, right? So not only are you managing the scale down there, you're actually sort of really capturing this dynamic behavior of a fluid particulate system on the scale that it should be captured. And so what it means is that this high fidelity physics and chemistry allows us to sort of resolve the hydrodynamics well enough, the temperature distributions. And on top of it, it also allows us to capture reactions happening. Now, these reactions, as I was mentioning, can happen in your gas phase, or they can also happen inside of your particles itself. And that is what makes us as unique, because we can combine all these together in one single simulation setup without the need to import any third-party libraries. Now, one major advantage of Barracuda as well is that Barracuda solver was built from ground up to be a multi-phase flow solver, unlike some other commercial CFD solvers, which started off as single-phase solvers and then evolved into multi-phase flow solvers. So, if you put all of this together, what actually it means is this package allows you to solve problems on a small scale to a large scale. And this is actually powered by our GPU acceleration. And Barracuda and at CPFD, we were one of the pioneers in terms of adapting GPU parallelization for a solver. And that's what sort of completes a package where you capture all these physics, but not only on a small scale, but you can scale up to much larger domains, and then get answers in reasonable amount of time frame, right? With that said, again, just to kind of summarize down here, obviously, if you have a well-validated CFD model, the biggest advantage is you can actually see what's happening inside the reactor, which is not quite possible all the time, with experimental setups. Once you're able to visualize things, you either identify issues with the design or maybe your operation, and then you can start thinking about how would you optimize them and fix those issues, right? And essentially, the idea is that you can do all of this sort of on a digital twin. So maybe you carry out some experiments on your lab scale. You build a small CFD model, you validate it, looks good, and now you're trying to scale it up. But you're doing all of this scale up on your digital twin rather than on your real system. So you solve these problems inside the software, you gain the confidence before you start actually building up some equipment here. All right. With that said, let me jump straight into the model we're actually going to look at today. So the CFBC model that we're looking at for this application model is a 50 kilowatt CFB combustor that was taken from an experimental work. Again, all of this model and the conditions are publicly available, and we do provide references both on our website as well as in the presentation down here. So this particular riser section for the CFBC was taken from an experimental work. All the geometry and the operation parameters were also obtained from that literature. The riser section is 4.2 meters tall here. And basically, what we do is we initialize the system, as you can see down here, with a bed of ash and calcium oxide particles. So this is an initial condition that you place this bed down here, and then you sort of inject primary air coming from the bottom of the riser. And then, as I was pointing out previously, you also have secondary air stage combustion that happens. Now, coal is injected from the inlet on the side down here. The bottom section of the wall is adiabatic. The section of the wall colored in pink down here is a thermal wall condition. So that is a thermal wall at 298 Kelvin. And we also use basically a thermal wall resistance. So this is a relatively new feature in our software over the last year or so. So now we can actually define conductive resistances to your walls, which is what we use down here. And as you move up, basically you have a pressure outlet through which, or a pressure boundary condition through which basically your solids and your gas are allowed to leave. Now, in the experiment, it was measured that the hydrocyclone is almost 100% efficient. So therefore, they do not include the hydrocyclone in the modeling, neither we do. But the nice feature of our software is this boundary condition called as the BC connector. So it stands for boundary condition connector. In this particular case, I'm actually connecting the pressure boundary condition with the recycle inlet down here. So this is not a CAD model. This is just a numerical implementation. That's what the solid backline is implementing. It's visually telling me that all the solids which are actually going to exit out of the riser section will be brought back by the solver and injected back into the recycle inlet down here. And all of this is done without actually physically setting up a CAD or gridding it. And so you'll see that when we actually, for several of these reactors, this is actually a pretty typical boundary condition that is used, and it's quite robust in nature. Right. With that said, before I jump into some results, I just want to take a moment and briefly look at some of the chemistry that has been inputted in this model. First thing is we have a custom kinetic model for about 28 homogeneous and heterogeneous reactions, so both gas phase as well as discrete phase reactions. We have put together these reactions from several literature sources. We try to provide them, and I'll show that when I open up the setup, we try to list some of the papers as we can. But we have also used some of the experience over the years where we have, implemented these reactions in several of our work down here. And so we have taken all of that experience to combine with publicly available reactions and kinetics, and then we've tried to implement them down here, right? And then before I begin, the volatile composition was taken from the given paper down there. And the first set of reactions that happen inside of the reactor is as soon as sort of solid coal particles come in, there's the devolatilization process happens, right? So, and devolatilization happens, and primarily what you end up producing is methane, CO2. You basically have, some amounts of ammonia, hydrogen cyanide, and hydrogen sulfide that come out as well. So this is sort of the first set of reactions that would sort of take place. The coal comes in, devolatilization happens, gas is released. Once they come out, then you have sort of your, this fluorovolatile combustion that takes place, right? So basically your methane, reacts with the oxidizers. So you have methane oxidation going on, CO, hydrogen, and water gas shift reaction that take place, right? All of this, again, remember, they're all taking sort of place simultaneously. It's not a staged thing as I show in this picture. This is more to sort of break down what's happening inside the reactor here. All right, as we move on, then we start looking at nitrogen chemistry. And this is quite interesting because this is where your pollutants are formed, right? So there's hydrogen cyanide and ammonia that come in. If they do come into contact with the oxidizer, then essentially you have NOx formation that happens. So you basically form both your nitric and nitrous oxides. And then once you form them, hopefully you can reduce them further. And that is where sort of the stage combustion comes into picture is, can you get these NOxes to basically reduce further, right? And then recover nitrogen out of that, which is what you ideally want, to be leaving your riser section. Then there is a set of reactions which are taking place in the discrete phase or your particle phase. So this is all. So once the gases leave out of the fuel material, you're left with primarily char, and char gasification and combustion reactions also take place. So the brackets for the S represents that this is a solid material. That's what is a representation here, right? And then you also have NOx reduction happening with char. Again, hopefully you don't produce a lot of NOx, but if you do produce, you want to reduce it further. And then importantly, once sort of all the carbon material also leaves, there's also some trace elements of solid nitrogen, sulfur nitrogen, and so on that you also want some sort of gasification oxidation reactions to occur. And again, this is not all the reactions inside the system. I've just taken a few of them and try to sort of divide them and explain them in terms of their importance down here. And last but not the least, the hydrogen sulfide that comes in, right? This forms basically sulfur dioxide, and this is a pretty bad pollutant. So this is where actually sort of the solvent material we place inside the reactor, which is calcium oxide. We want that to sort of capture this pollutant and then maybe potentially convert into calcium sulfate. So that reaction is also included in this current setup. With that, let's jump and look at some results. First things is sort of a numerical validation. What I'm showing down here is the average fluid temperature along the height of the riser. And the black line are results from Barracuda, and the blue circles are from the experiment. The first thing we do is we sort of compare how the temperature variation looks along the height of the reactor, and we see quite a decent match between the experiment and the simulation here. Then we also compare some gases, mole fraction of gases that are leaving the outlet or the pressure BC. So we're looking at mole fractions of O2 and CO2 on a dry basis, and again we see a pretty good match, with the results down here. Again, remember that in the paper they use a different set of kinetics, whereas we have used our own custom set of kinetics to model this. With that, now jump into some interesting results here. So I know there's a lot of sort of animations playing around, and I'll go them stepwise from the left to the right here. The first thing that I'm looking at in this animation is basically circulation of both devolatized coal. So this is your ash and your calcium oxide with the coal feed. The first thing I'm looking at, as I'm post-processing this, and again, different engineers can post-process these results in different ways. If I were running the simulation, this is how I would post-process it, and this is the kind of information that I would like to extract from the simulation. So first things is I want to see that is my circulation going all well enough in the system, right? Because circulation of this ash is quite essential, because that is what is responsible for your heat transfer along the height of the reactor. And I do see that the fluidization looks quite well. I'm able to circulate the solids from bottom to the top. I don't see any gaps or sort of solids leaning towards one side of the reactor and so on. So that's the first thing. Then what I'm showing in the second picture down here is as soon as the coal comes in, and I'm coloring these particles by the fraction of the volatile gases in there. So you can see that initially the particles are all red in color, so they have all the volatiles in them. But as soon as they enter the reactor, devolatilization takes place, the gases come out, and you can see that the particles turn more aquamarine, right? So now they are mostly contained of solid char, essentially. And that's what I'm trying to color down here in the third picture. So essentially, these particles come in, the volatile gases leave, and then you're left with char inside of these solid particles, and then some of your char gasification and combustion reactions are taking place along the height of the reactor down here. And last but not the least, this is quite interesting. So what I'm showing down here is calcium sulfate particles. They initially start off pretty blue, but as time runs on, as you get closer to 60 seconds, you can start seeing that they're capturing all the sulfur dioxide, essentially. And this is what we want. We want this solvent to capture some other pollutants that come out, and this, it seems like it's happening inside the system right here. Right. With that, now let us look at some gas phase animations. And the first thing I'm going to do down here is not necessarily go into details. I'll do that on the next slide here. I just wanted to highlight the fact that this is a transient simulation. So again, this is a transient simulation, essentially running with the full chemistry inside the system. So what I'm showing down here is various, sort of volatile gases that come out, and then the oxidizer and some products that are forming out. But it's a dynamically evolving system, as you can see from the volume fraction or the plots down here, or the mole fraction plots that are shown down here. All right. One advantage with Barracuda is that mostly with engineering solutions, I do want my simulation to be running transient, which is what happens in real nature. But then when I'm starting to make engineering decisions, I want to average that data over, right? I want to average that data over time. Sometimes I want to average the data over space. And averaging over time within Barracuda is actually, it's provided inside the setup. So what I'm showing down in this animation is the same animation as on the previous slide, but now it's time averaged. So essentially, when I set the simulation up, I said from the 30-second mark to the 60-second mark, start doing a time average. So now you see that it's the same transients. There is still motion that is happening for the gas, but it's all average over time. So it's not as chaotic as it was on the previous animation. Now let's look at some details down here. The first thing to observe is basically the mole fraction of methane. So as soon as cold particles come in down here, you see that the devolatilization process happens, and right there, methane is released in the system, right? So methane comes out, and then you also have CO2 and CO, which are also volatile products, and they're also formed through other reactions, but you see red regions down there where the devolatilization process happens. All right, so once this happens, you basically have your oxidizer, or air coming from the bottom down here, and you can see that most of that oxygen in the air actually is consumed right here. You see a dark blue mark right there, where sort of the devolatilization process is happening. And it seems like most of the primary air, if not all, is being consumed sort of in this dense to dilute section, and sort of a dense to sort of transition section, and where it reaches the cold inlet. All right. And then I also have a secondary air inlet through which I'm actually injecting additional air, and we'll look at that in a second. And then you essentially, through the reactions, you form some water vapor. All right. So that is basically on the combustion side of the volatiles. What happens when we start looking at nitrogen reactions? And this is important, as I was mentioning, from a NOx formation and a NOx reduction point of view, right? So again, if you look at where the coal inlet is, right where they're coming in, both ammonia as well as hydrogen cyanide, these are volatile gases that come out from a fuel particles down here. When they come out, essentially what happens is, they do react with the oxygen coming in from the primary inlet. So we try to keep this region fuel rich, essentially, to minimize that, but nevertheless, we do see some oxygen reacting with that, and then what that results in is formation of NOx. So what I'm showing down here is contours of NOx, and you can see that right here in this region is where so the high concentration of NOx is forming, right? Essentially, and so once this NOx forms, ideally I want to be able to capture this NOx or completely reduce it using my air from the secondary air inlet. And if I point out towards the wall down here, I do see that some of the air that comes in from the secondary air inlet, that does reduce the NOx. So you can see that it goes from yellow to green to bluish over time, pretty much. However, the unfortunate thing is that, at least looking at this results here initially, it seems like the penetration of the secondary air inside the reactor is not happening very well. So therefore, the oxygen comes in, but if it's not penetrating deep enough into the reactor, and therefore it's only able to reduce the NOx more aligned towards the side of the wall down here, and you do produce nitrogen over that side essentially. But ideally, if this can penetrate deeper inside of it, I can capture more, or I can reduce more of the NOx gases. And so again, if as an engineer I'm looking at this potentially could mean either a design improvement I can think about, or an operational improvement that I can think about, right? So this is how I would sort of use my results, post-process them, gain insights, and then subsequently, start thinking about improvements to my process. With that said, I think I come to the end of my presentation, and now I'll take a moment actually to actually demo this model. In the interest of time, I can't go over every single setup that is there inside of the model, but I'll try to highlight a few key ones. All right. The first thing I'm going to do is I'm actually going to go into our website down here. So this is our website, cfbsoftware.com. If you see, I'm not logged into the system currently. If you're a user, you actually have a login that you use to log in, and then you can access some of our resources. I've not done that on a purpose down here. Let me go back to the section which says resources and then application models, right? So this is where all application models live. If I click on that link, it takes you to this page. And so as Zinaj was pointing out, we have a variety of application models ranging from upstream oil and gas to hydrogen production and cement and so on. We actively work on these application models, and so we will continue to add to these models available right now. And the first thing to see is I'm going to click on this circulating fluidized bed combustor, which is the application model we're looking at today. If I click on this model, I see that there's a general overview that is provided initially in terms of like the higher level picture or of of what you will find inside this post. When I click on this access model, you see that I've still not logged in. So this is still available on a public site down here. What it does is it actually provides sort of the entire post to the general public. You do not have to log in to see this. So we start off with the general introduction, sort of a high level view. We quickly jump into what we're modeling today. In this particular application model, we provide the details, the references where we have taken this information from. Sort of, it almost sort of reads like a brief report for you. Talk about the model itself. And then importantly, right, for many of these models, we always have chemistry involved in them. And so we take a lot of time, invest a lot of time into actually bringing this out information, right? So reaction kinetics is a pretty important subsection for our post. So here we list all the different reactions that were input into the system. We also give out sort of all the rate constants, and then sort of the finally the Arrhenius rate expressions and so on for every reaction that's in there. Once we do that, then obviously we jump through some results. We looked at some of them today. Wherever we can validate, we try to validate a simulation, and then we jump into this modeling instructions. So this layout is pretty common. If you don't have chemistry inside of the simulation, obviously that section isn't there. But once you come to this modeling instructions part, here is where we provide you the support files, where it says download the support files. Once you click on this link, this is where you need to have your login ID as a registered user for Barracuda to be able to access those files. So I'm going to log in as myself down here. And once I do that, it actually takes me to this zip file link. Let me download this here. And let me open up this in the folder. And I'm just going to unzip this guy here. All right, that done. So here's the folder inside of that zip folder. And what you see in here is basically, our project file. We provide you with the STL file, the project file, and essentially all the setup that is needed to set this model up. Let me double click this guy and open up to bring up Barracuda. All right, so basically, as you sort of go through some of these items, you see that the setup is all completely done for you, right? The first thing usually you want to do is generate the grid. We usually don't do that because this is a small scale reactor, but generally for some of the larger scale reactors, the grid takes up a lot of memory. And so the zip file size becomes large. So therefore we avoid doing it, but it's pretty straightforward. The first thing you actually do is you should click on generate grid down here. Even if you don't do it here, when you try to run the simulation, the solver will ask you to sort of first generate the grid. So it's no problem even if you don't do it at this step. So with that grid generated, the first thing I'm going to look at is the global settings. So this is actually a thermal simulation. This is compressible flow, and then base materials, right? So we have provided you with all the base materials that are available down here. One thing I want to point out is for the volatile components down here. So when you come here, it is in solid phase, but essentially this heat of formation number, getting this right is quite important. And it becomes especially important when you start looking at biomass or industrial waste, right? This is a hard to get number. So, but this actually controls essentially how much heat that is coming out of the system down here, or how much heat has been taken away, right? So this is something that again, we have calculated based on the volatile, sort of the solid material composition itself from approximate and the ultimate analysis. So we come up with this number, and we have provided that in the setup down here for you. Then what we look at is particle species here. If you see down here, I have got 3 particle species listed. And inside of the presentation, I was only referring to 2 particle species, right? I was referring to cold feed as well as devolatilized coal. So first, let's look at what those are. Cold feed is essentially your, all the solid components along with the volatiles that come in. So this is actually your fuel in the system. Then you have sort of devolatilized coal, which is essentially mostly ash with a bit of CaO inside of it. And this CaO is what is actually capturing your sulfur components. But however, if you want to run the simulation only using ash, where you do not have that sort of the CaO, you can also do that. And that's why we have this additional particle species, which is not used currently in the setup, but if you want to use it, it's a pretty easy switch. All you do down here is you come here in the initialization aspect of it, and you basically change what is the species that you want to initialize it. We just say, I'm going to initialize this with ash, right? So that actually tells you, like a one-on-one comparison with and without sort of the calcium oxide there to capture. All right. With that, let me quickly go into some boundary conditions. Flow BCs, obviously, like I said, you have your primary air, your secondary air, your cold inlet, your secondary air. Importantly, here is where we have the returning air, right? This is where that BC connector boundary condition is used. And so if you see for particles, usually inside of a setup, for those who are familiar with Barracuda, right, we basically set up our fluid properties, we set up our particle properties, and then here for particle properties, though, I'm saying use that BC connector data. There's no independent boundary condition being provided to you down here. Just use that information that is coming from the pressure outlet. And where is that setup happening? That setup's happening right there under BC connections. So if I click on BC connector, here is where I'm saying the input connection from my BC is from my pressure BC. I'm going to take the solids that are coming in from there, and I'm going to inject them into the recycle inlet down here. So this is where that setup happens. All right. With that, very briefly, I will look at some of the chemistry, and let me see if I can do a good job on actually, having these side by side. Let me just go back here quickly. If I can do this. All right, so let me just take the window down here. Okay, so if you primarily see, right, firstly, sort of all your, the sort of the reaction setup, all your, kinetics are actually all defined down here in the rate coefficients manager. You see that obviously a whole bunch of them are all sort of your volume average chemistry, but then there are some user-defined reactions as well. So generally within Barracuda, if it is in an Arrhenius form, you can actually define them directly within the GUI. There's also a polynomial base or a table base that can be input. But if you have an expression which doesn't conform to any one of these default issues, you can always define them as a user-defined chemistry expression, and which is what we do down here. And we also make sure that when we do stuff like this, we try to highlight that, we explain that, we give a bit more information inside of the post about that, right? Obviously there are 28 reactions down here, so we cannot go over every one of them in the post. But wherever we feel that extra information needs to be provided, we do that. Last but not the least, importantly, if I go to reactions, obviously here's all my volume average chemistry being set up. So if I go back to the post down here, this is my first reaction, and that is exactly what you see set up down here. So this corresponds to the order. Again, we try to make sure that the order is also respected with the post as well as the setup, right, as much as we can. Last but not the least, you also have these discrete reactions as I was talking about, right? So all of this again is combined in a single setup. You don't have to import a third-party package to be able to define this, or you don't have to define a user-defined function, through a little code to sort of include this in the simulation. So all of this in a single window in a single setup. And here is sort of my devolatilization reactions that I was talking about are defined. All these are discrete reactions, and they're defined on the solids component of the volatiles down there. All right. With that, then all that remains to be done is you come down here and then you say hit run solver. Now you can run this with a GPU, without a GPU. You can run this if you have multiple CPUs. You can also use that. I do happen to have a GPU, so I'm going to just use that here. And once I hit run, it goes essentially. It's all set up for you. You don't need to do anything sort of other than generating the grid to be able to start running these simulations. All right, so once that happens, let me stop this simulation because I've already run this so that I can open that up very quickly. And so here is where my, okay. One thing I want to do is, obviously this is all the simulation that I've already run up with. If I quickly do some post-processing, I can look at some results here. Let me bring this open. So here's all sort of my simulation results available at 60 seconds. Let me do just some simple contour plots. One thing I want to do is initially it only loads the simulation file at the last time step. If I want to load all time steps, I go down here. and I say refresh reload. Again, if you're not familiar with some of these steps, don't worry. We do go over them in our training. We also have a lot of support posts to go over tech about post processing. The idea is, just to show that how simple it is with all the setup available. Once you run, I can come here and start do my post processing straight away. So I've created multiple frames so that I can start looking at results adjacent to each other. And if I do that, here are all my results available, right? So I can come down here now, start looking at, I was talking about these time average solutions. So I have mole fractions, which are averaged over time. So if I come down here, maybe I want to plot my NOx, basically, essentially the gas. So this is, I'm looking at NOx form in this simulation. And then maybe down here, I want to look at some of the hydrogen sulfide that comes out in the system. Okay, and if I want to change the scale, obviously I can change the scale to look at this thing, right? So again, all of this is available. So if I go back to the post quickly, we do provide post-processing instructions completely. If you scroll all the way down after setup, you see that all the post-processing instructions are completely provided for the pictures and the animations that we have in the post. So we go stepwise in detail, so you can use these to replicate not only as a learning exercise, but you can take this information to some of your other models. Last but not the least, I just want to show you one quick thing before I end this demo here. Is I've set up another case here called test. If you look at it, I just have a simple cylindrical reactor, and let's say I want to use the chemistry that is available from this CFB application model post, right? All I have to do is come to this chemistry option down here, say import materials and chemistry. I'm going to browse there and go into this setup that we just looked at. So I'm going to say, open this project file, get me all the materials from that project file, basically bring all the materials defined. Also import all the chemistry that is available inside of it, right? Once I do this, I then see that all the base material properties that were defined in the CFB are available now for this setup, and all the chemistry is also available, right? All the reactions, all the kinetics, just by clicking a couple of buttons. Now, this is actually sort of what we want to empower our user with, is basically all this information, such that not only can you use these with the model we provide, but you can take this and use on your own models. Right, with that, I'm going to turn this over to Niraj.
Perfect. Thank you. Let me grab the screen from you. Okay. Thank you, Shank, for a fantastic presentation. I'll let him take a quick breather before we go into the Q&A with our remaining few minutes. In the meantime, I'm going to go over CFB's offerings. Please, again, use this time to ask questions in the side panel. Thank you so much to everyone who's asked questions. I can see here we have a couple dozen. We'll only be able to get to a couple during the Q&A session. The rest of them we'll make sure to follow up with you via email. So for those of you interested in trying or using the software or engaging with our company, the primary way that we deploy the software is through software licensing. So this would be your team using Virtual Reactor on your premises. We offer both single site licensing as well as for larger multinational companies, we do offer enterprise licensing. Licenses are usually cloud served, but I understand some companies have very tight security, so on-prem licensing is also available. We also offer engineering services, and this would be our CBFD staff engineers working hand in hand with your engineers. This can be either project-based or broader collaboration. This would involve us setting up and running these models, and again, working very closely with your team to meet your project goals. And then we also have things that are kind of in between, where there's a program we call the Quick Start program, which would be our engineers setting up, calibrating the first model, and then delivering it to your team, who then takes that model and then does with it what they see fit. So this would, again, still involve us working very closely with your engineers, but this is maybe a combination of like initial services with software licensing. We also offer new user training we have our online training course, but we also can do custom on-site training as a small company, we can be pretty flexible, so we're always looking for ways to deliver the software in ways that are most convenient to our customers. Um, and finally, we also do work with a variety of research consortiums. So again, that's the benefit of working with a small company, is that we are flexible, that we can find ways that make the most sense for your team and meet your timelines and budgets. A quick word on upcoming events. So we have our online training course, our Barracuda Virtual Reactor New User Training. There's a class next week, and then the next one is in December, and our 2026 dates will be announced in the next few months. The online class is an ideal way to try the software. If there are those of you in attendance who are not quite familiar with Barracuda Virtual Reactor, this is a great way to learn about the software, to get an idea of what best practices are and basic usage, and also interact with our staff engineers who do leverage decades of experience and bring a lot to the table. And then for those of you who are very familiar with the software, it doesn't hurt to get a refresher. So if you want to take the course just to kind of get caught up, and take the opportunity to talk one-on-one with our brilliant engineers, we highly recommend you do so. I do believe we have a few seats available in our October 6th class, so please reach out at the earliest convenience, and we can see if we can get you in that class. If not, the December class also has some seats available. We work with PSRI, a research consortium based out of Chicago, at their fluidization seminars. They have we usually deliver the modeling talk section of their talk. It's seminars for the kind of introduction to fluidization for engineers working in industry. We will be exhibiting and presenting at ERTC in Europe, and then we also will be sponsoring the PTF, the Particle Technology Forum's Student Poster Awards, once again at the ASCG annual meeting in Boston, November this year. And then a final quick note, we are once again having our users conference. I think this is the 6th iteration of our users conference in Chicago in 2026. So please save the date if you are interested in attending June 24th, 26th. If you are interested in learning about speaking opportunities or sponsorship opportunities, please feel free to reach out to me or to anyone on our team. And with that, we can get into the Q&A session. We have about 6 minutes or so here to answer some questions. So I don't think we're going to get to all couple dozen of these questions, but again, we'll make sure to follow up with an email. I'm going to start here with the question asking, could this be modified for MSW or biomass? MSW, municipal solid waste, I believe. And if so, how? Shashank, would you like to take that one?
Yeah, no, absolutely. In fact, this is actually a great setup to do that. All you probably have to tweak is a few of those reactions itself and some of the kinetics. But generally, what you'll observe in literature is some of the char sort of gasification reactions. All of those are taken from sort of coal combustion in general. So yeah, I mean, several of these reactions can be used as is with a few tweaks here and there.
Okay, fantastic. Next, I'm seeing a question here. Are the reactions solved on the GPU or the CPU? And I can answer this one. So the software started parallelizing various calculations about 15 years ago or so to the GPU. We were a very early adopter of the GPU, and chemistry was the last one to get parallelized. So there's various ODE solvers that make up the that are components of the MP-PIC method, and the last one to be fully parallelized was chemistry, and it was right before I joined the company, so maybe 7-8 years ago. So yeah, all of our ODE solvers are fully parallelized in GPU. So those chemical reactions are solved on the GPU. Next, we have a question here asking, how can I try this if I don't have a software license? Yeah, so if you are interested in trying to run this model and you're not yet a licensee, please reach out to us at info@cpfd-software.com, or reach out to anyone who's presenting today, either myself or Shashank, and we can help you get set up with a trial license. I have another question here. Hello, doctor. Thank you for the presentation. What is the difference between CFD, DEM coupling, and MP-PIC in general?
I guess it boils down to how sort of the particle interactions are treated. Essentially, in DEM, these are sort of resolved on a more explicit scale. Whereas we use particle stress models within MPPIC to resolve that. Again, the difference is that DEM, while it can be more accurate on smaller scale models, scaling up is a challenge when you start accounting for particle to particle interactions where you have tens and millions of particles, and that is where MPPIC truly stands out. Is not only is it accurate enough, it's also scalable.
Fantastic. And then another question here asking, can I change the geometry to a different design? Shashank?
Absolutely. I mean, I guess once, the last thing I was showing in the GUI was an attempt at that. I mean, if you can always replace the existing STL file, bring in your new STL file, and the setup remains the same. All you have to make sure is you make sure that the boundary conditions are defined on the faces that you want them to be defined, and make sure that sort of the dimensions and everything are accounted for, right, in terms of where you're placing. If you have any post-processing planes and stuff like that, just want to make sure that all of that is taken care of. But absolutely, you can remove the existing geometry in the setup, bring in your own geometry, and continue finishing running that model.
Okay, I think we have time for a couple more questions here. Here's, I think, a question and how is the concentration of the volatile expressed, i.e. specific surface, and then a follow-up, sorry, I meant the solid materials.
Can you say that again? I'm not quite sure.
How is the concentration of the volatile expressed, i.e. specific surface?
So okay, so the volatile composition is actually provided by inside the paper. So they provide us with an ultimate and approximate analysis, essentially. So all of that is listed and available, which is what we actually use to define here. So when you define sort of this a particle of the fuel, that is where we're defining how much mass of it is solid carbon versus how much of it is going towards gases, right? So all of that is taken into account from the provided information.
Great. And then here's another question. Can I add my own reactions to this model?
Oh, absolutely. Yeah. I mean, you can. I mean, that's exactly the idea. This is not meant to be taken as it is. This is just a starting point for you to show what can be done. You can absolutely add your own chemistry, expand on it. If you have your own data, own information for volatiles, you can also replace that.
Perfect. And I think we have a last question here. A bit of a long one, so hopefully we can get to it. Have you modeled a system in which the circulation system in which combustion occurs to a system in which pyrolysis occurs using superheated methane in the fluidizing and heat transfer media? And there's a few clarifications here. This is then a non-combustion fluidized bed circulating pyrolysis system. The carrier gas can be recycled and in doing so reheated. So yeah, have we modeled something like that before?
Not really. I mean, personally, at least I'm not aware of it. Maybe others, because we do a lot of projects with a lot of different clients. So I'm sure others within the company have more to share there. But I personally haven't looked into it. But again, if that is something of interest, reach out to us. We can talk more.
Absolutely. And I think from my knowledge, I think we have modeled non-combustion CFBs with pyrolysis, but I don't think there's anything publicly available, like nothing non-proprietary. But yeah, we'll continue this conversation separately. And I think with that, we're going to put an end to the Q&A session right here. Apologies if we haven't gotten to your question. I will make sure to follow up with everyone sometime this week for all your questions. And thank you so much for all the wonderful engagement and for all the thought-provoking questions. And then thank you as well for attending. This was the first in our webinar series for application models, and we look forward to hosting many more. Thank you and goodbye.